Okay, so in this video, we're going to go through sample question 25 from the Society of Actuaries, ExamP, list of sample questions. Right, the question reads, a blood test indicates the presence of a particular disease 95% of the time when the disease is actually present. The same sample test indicates the presence of the disease 0.5% of the time when the disease is not actually present. So that's a false positive. 1% of the population actually has the disease. We want to calculate the probability that the person actually has the disease given that the test indicates the presence of the disease. Okay, so this is similar to some problems that are a part of the SOA ExamP list of sample questions that you might have already done. However, it is admittedly a little bit more complicated. They don't just give you the information in a straightforward way. So first, let's see what the question is asking of us. We want to calculate the probability that a person has the disease, so probability that somebody has the disease, given that the test indicates the presence of a disease. So I'm going to say that you tested positive for it. Right? That's what it's asking us to calculate, which that's a conditional probability, right? So that formula is we want the probability that somebody has the disease and tests positive for it divided by the probability that any individual person tests positive for it, which is probability of P. Okay, now first let's see the information they give us, because it's not straightforward. It's not in a chart. It's not just, hey, here is what we know. They, talk about it. So let's write that down. The probability that a test indicates the presence of a particular disease is 95% of the time when the disease is actually present. So it's saying that given the disease is actually present, you get a positive result 95% of the time. So the probability of a positive result given that somebody has the disease is equal to 0.95, which would imply the probability of a negative result, right, not P, or P complement, given that somebody has the disease is 0.05. The probability, and then it finally says, the same test indicates the presence of the disease 0.5% of the time when the disease is not actually present. So a false positive. So the probability that you get a positive test given you do not have the disease, well, that's equal to, what is that equal to? 0.005. And the probability that you get a negative result, given that you don't have the disease, would then be equal to 0.995. And we just add zeros at the beginning of these. Okay, so this is the information it gives us. Unfortunately, none of it seems to be the two pieces that we need. So clearly this is going to be a Bayes theorem problem, right? Bayes theorem problems are kind of apparent when we're given when we're asked to find, in this case, the probability of D given P, but what we have is kind of the reverse, the probability of P given D. All right, so let's figure out how to actually separate this problem. You should know at this point how to deal with a Bayes theorem problem. And I left out one piece of information. 1% of the population actually has the disease. So we also know the probability of having the disease is equal to 0.01, while the probability of obviously not having the disease is equal to 0.99. Okay, so let's see how we want to organize this information, right? So our numerator, right, from Bayes' theorem should be the following. The probability of having the disease multiplied by the probability that somebody tests positive for the disease given that they have it. While the denominator is every potential possibility that somebody has the disease. Every potential possibility where somebody can test positive for the disease, right? So they can either test positive for the disease while actually having it. So that's the probability of having the disease times the probability of testing positive for the disease given that they have it, plus the probability that they test positive for the disease given that they don't have it, multiplied by the probability that they don't have the disease. So probability of D complement times probability of testing positive given you don't have the disease, right? And this is just a very common application of Bayes' theorem. We can then use the information here, right, from the actual problem to fill in what we know. So I'm just gonna write this stuff to the side, right? So in our numerator, we should have, I'm just kind of, right, little arrow there, probability of having the disease, so that's 0.01, multiplied by the probability of testing positive given that you have the disease. So that's 0.95. Divided by the probability of having the disease. So that is, let's see, probability of, I can't do that. Probability of having the disease, which is 0.01 times testing positive given that you have the disease, that's 0.95, plus the probability of not having the disease, which is 0.99, times the probability of testing positive given that you don't have the disease, which is 0.005. All right, and calculating this, that's something I can just put into the TI-30 calculator. Let's see, in the numerator, 0.01 times 0.95. In the denominator, 0.01 times 0.95 plus 0.99 times 0.005. And that gets me a final answer of approximately 0.657439. And since the answer choice is round to 3 decimal places, I'll just write that as 0.657. Which would be answer choice B. Okay, so another way of kind of looking at this problem, rather than just going straight into it, is in a few of my previous videos, I've kind of done a chart, right, for organizing information. So let me see if I can do a similar thing here. Okay, so here, if we made a box where in these two columns, it's either you have the disease or you don't have the disease. So since 1% of people have the disease, this row should add up to 0.01, right? And I'll just kind of write that kind of small to the side, 0.01. Well, this should add up to 0.99. And here is testing positive for the disease and not testing positive, right? Testing negative. And what we're told is that, let's see, 95% of the time where the disease is actually present, so that means 95% of all of these cases, you do in fact test positive for the disease. right? Which would imply of all cases, right? Because the intersection of these, like this box actually represents the probability of having the disease and the probability of testing positive. That would be 0.95 times 0.01. So that box would be 0.0095. And that would mean that this box, the probability of having the disease and not getting a positive result when given a test is 0.0005. Okay? And then it says the probability of testing positive given that you don't have the disease is 0.5%. So the same way we got the information for these two boxes, we can get the information for these two. So that's going to be 0.99 times 0.005, and this is going to be 0.00495, testing positive and not having the disease. And this is going to be 0.98505, right? Probability of not having the disease and not testing positive. Okay, now why does this help us, right? It's a bit more organized if you're not able to immediately go into this problem. So when the question asks the probability that a person actually has the disease given that their test results indicate the presence of the disease. So the test results indicating the presence of the disease is this column, right? That's my denominator. And the probability of actually having the disease of all the people that test positive, that would be these guys right here. So the basic formula for probability is number of ways something can happen over kind of total number of ways anything can happen. So this is going to be 0.0095 over this whole column, which is 0.005 plus 0.00495. And you might notice if you kind of did this piece by piece that this is just the Bayes' theorem formula without actually knowing what the Bayes' theorem formula is, right? This is just understanding how charts kind of work and how intersections work. So calculating this, I should get the same answer, right? So 0.0095 over 0.0095 plus 0.00495. And I get the same answer of approximately 0.657. So those are two separate methods to getting the same answer. And I think both work equally well. I would use both. I do use both. It kind of depends on the problem, whichever option I see first and whichever one I see is easier for me personally. However, both are completely valid and I think equally, like, neither one is easier than the other, right? Neither one's necessarily a shortcut. It's just different ways of seeing the problem. Hopefully that illustrates, the different approaches pretty well. If there are any other questions, throw it down in the comments. I'll answer them to the best of my abilities. And if this video helped you out, hit the like button. Subscribe, because that definitely helps me out. Other than that, good luck, guys.